Hi everyone, today we'll be looking at day 2 of section 5.6, inverse of a function. In example 4, we're going to work to find the inverse of a cubic function. That function here is negative 1/2 times the quantity of x plus 1 cubed minus 4. We're going to determine whether that inverse is also a function, and then we're going to work to find it algebraically. So we're asked to use a graphing calculator to plot g of x, and we can see some things. We can see that negative 3, 0 is the x-intercept, also that 0, negative 4.5 is the y-intercept, and if you remember from the previous sections when we're transforming, you can see that where that point normally would be at 0, 0, we have shifted 1 unit to the left and 4 units down, so we are now at negative 1, comma, negative 4. If we were to graph the inverse of this function, is it also a function? We answer that question by looking at the horizontal line test. When we draw in an infinite number, I've got 3 here, but an infinite number, do we pass that through that function only once? The answer is yes, and so not only does it pass the horizontal line test, but it also tells us that the inverse is a function. While we're here, let's just take a moment to plug in 0. Down below, if you see, what is g of 0? So negative 1/2 times 0 plus 1 cubed minus 4. That'll simplify to negative 1/2 minus 4. That is negative 4.5. So when we plug in 0 for x, out comes negative 4.5. That tells us that our y-intercept is negative 4.5, and you can see that on the graph. Now let's work to find the inverse. So the first thing that we do is we take g of x and we substitute in y. And then we take the x and the y and we switch their positions. We're now going to work to solve for y, and we take the order of operations and we work in reverse order. So we're going to add that 4 to the left. Now we're going to multiply times the reciprocal of negative 1/2, so we get negative 2. And I'm going to leave that negative 2 out there for the moment. We want to undo cubing, so we're going to take the cube root. And finally, we're going to subtract 1 from both sides. So let me just pause for a second to make sure that you can see that. The reason that I chose not to distribute that negative 2 under the radical sign is that it helps me to see that originally my function g of x had a horizontal shrink of 1/2 and a reflection over the x-axis. Now with that negative 2 out in front of x, I can see that that's going to be a horizontal shrink by a factor of 1/2 and also a reflection over the y-axis. So our inverse function of x is going to be that cube root of negative 2 times the quantity of x plus 4, and then we're going to subtract 1. You can also see that originally we shifted down 4 units, so a negative 4 units. Now we are shifting horizontally left 4 units. We also originally, that x plus 1 said we originally shifted 1 unit to the left. Now we're shifting 1 unit down. So just keep in mind when we're talking about inverse functions, everything about x and y switch positions. Now that we have that inverse function, let's go ahead and plug in 0 for x, and you can see down at the bottom here, if we have 0 plus 4 times negative 2, that's going to give us negative 8, and the cube root of negative 8 is negative 2. We still have the negative 1 on the outside, so when we subtract, we get negative 3. That means that when we plug in 0 for x, we come out with negative 3. So the y-intercept for the inverse function is 0, negative 3, but that also tells us that we can talk about x-intercepts. For the original function g of x, it's going to have that x value, negative 3, which was the y-intercept for the inverse, and what was the y-intercept for the original function is now the x-intercept for the inverse. In example 5, we're asked to find the inverse of a radical function. Let's first take a look at how this thing is going to graph simply by plotting some points and getting an idea of inverses, and then in our next section we will solve this algebraically. So if we plug a negative 6 in under the radical sign, we get something undefined because negative 6 plus 5 is still negative 1. We can't take the square root of negative 1. But negative 5 is okay. We'll get 0 under the radical sign, and that'll leave us with a negative 8. So negative 5, negative 8 is a point on our graph. If we go with negative 4 plus 5, that's 1 under the radical sign. The square root of 1 is 1, times 4 is 4, and 4 minus 8 gets us to negative 4. To go to negative 1, you might ask why not negative 3 and negative 2? We can, but negative 1 is going to give us a nice value. Let's see what happens. Negative 1 plus 5 is 4. The square root of 4 is 2. 2 times 4 is 8, and 8 minus 8 gets us to that nice integer 0. It means we're crossing the x-axis at negative 1, 0. Finally, for this graph, if we plug in 4, 4 plus 5 is 9. The square root of 9 is 3. 3 times 4 is 12, and 12 minus 8 gets us to 4. So these 4 points are on our graph. What we know at this point is that when we go to plot an inverse, we are going to have a reflection over the line y equals x. So that means everything about x and y switch places. So when I consider, before we've even algebraically worked out what the inverse of h is, we can take all of those x values that we had to begin with and now make them y values for the inverse. If that's true, then according to our work with inverses, we'll find that everything we already discovered for h of x initially is now going to become an x value. So if we go to plot that, we can see how the purple graph is going to be a reflection of the original, of the inverse, and we can see how those points are going to match up. Now let's go over to solving this algebraically. Okay, so let's work to solve this algebraically. When we take our function and try to find the inverse of it, the first thing we tend to do is take h of x and just simply replace it with a y. Then it's easier the rest of the way to switch the position of x and y and solve for y. So we're going to undo PEMDAS by adding 8 over to the left. Then we're going to take the 4 and we're going to divide. I'm going to express that as 1/4 just to give the sense that what was a vertical stretch is going to ultimately become a horizontal stretch. We've got the square root of y plus 5, so we need to undo that by squaring both sides. Now you see that 1/4 is inside the square. That's right in front of the x. That's our 1 over b. That's 4 is representing a horizontal stretch. And finally, we're going to have to subtract 5 from both sides. It's also possible, if you notice I took that 1/4 and brought it to the outside by squaring it. If you want to leave it on the inside and say that it's a horizontal stretch by a factor of 4, you can. If you want to bring it to the outside and say that there is a vertical shrink by a factor of 1/16, that's also going to be true. You might notice also that it doesn't impact the 5. Okay, so we should have that our inverse is 1/6 of x plus 8 squared minus 5. That's not quite complete though, because I want you to consider, remember, with the graph that's shown here, we have a domain that goes from -5 to infinity, and we have a range that goes from -8 to infinity. Do you remember how everything about our x's and y's, our domains and ranges, flip positions? Well, if we go back over and look down at the bottom at the inverse function, that's a parabola. Parabolas can be graphed from negative to positive infinity. But when we come back up and look at our range for our parent function here, the range goes from -8 to infinity. So that means when we talk about the inverse, the range of the original is going to become our new domain, and the domain of h of x is going to become the range of the inverse. So The way we're actually going to express this is the same looking function, but we're going to throw this restriction that's highlighted in yellow down at the bottom. We're going to say that yes, it's this parabola, but it only graphs when x is greater than or equal to -8. So when we plot that, we do get those points that we looked at from just plotting the original points, plugging in values for x, switching the positions when we come to the inverse. We do get that graph, but if we try to just jump over to some graphing technology and plug in the inverse without the restriction, we'd see a full parabola that goes from negative to positive infinity for our domain. In this situation, we want to restrict it because it needs to be a reflection of the original, of the parent function. I'd like to veer off to the class notes for a moment just to venture into compositions of functions. So if you want to take side notes, please feel free. This is a slight diversion from our textbook examples. Imagine that a car dealership is offering two sales. You can get $2,000 off the sticker price, or you can get 5% off the sticker price. Well, imagine that both were offered. Does order make a difference? You're looking to buy a $30,000 car. If f of x represents getting $2,000 off, and if g of x represents getting a 5% discount, meaning you're only going to pay 95% of that $30,000, how does it work if we first take off $2,000 and then take 5% off of that? Well, we can set up our function as taking off the 2,000 and then 95% of that. So when we plug in the $30,000, 30,000 minus 2,000 gets us to 28,000, and 95% of that gets us to paying $26,600. On the other hand, if we switch the order and take 95% of the 30,000 and then take off the 2,000, we can set our formula up like this. Insert 30,000 and we'll wind up with $26,500. You can see there's a difference of $100, so the order does make a difference when performing compositions. So the car dealership example dealt with compositions of functions, but they weren't necessarily inverse operations. Do inverse operations always undo each other? I'd ask you to think about addition and subtraction. Those are inverse operations. Think about your favorite number and add 6 to it. What's the value? Now take that value and subtract 6. Do you come back to your favorite number? Written mathematically, if f of x equals 1 and g of x is the other, if we take that favorite number and add 6, and then subtract 6 from that, that would be saying g of f of x. That is saying, what is x plus 6, and then subtracting 6. Those 6's cancel out, and we're just simply left with x. And we can go in the other direction as well. We can take x minus 6, your favorite number, subtract 6 from it, and then if we apply that f function and add 6 to that, again the 6's cancel out, and we're left with x. So in this case, inverse operations undo one another. But do performing inverse operations always return us to our original value? Let's think now about squaring and taking the square root. Those are inverse operations. If you take some number, square it, take the square root, you come back to where you began. Consider the value of -3. What if we squared -3 and then took the square root? We could express that as g of f of -3. So insert -3 into the f function, and what comes out? +9. Now take the square root of +9, and what comes out? +3. Therefore, we're looking at the absolute value of whatever it is that we plugged in. So inverse operations do not always necessarily yield the same value that we began with. It's like asking, is it an inverse operation to open and close a window? The window's closed, you open it, you close it back up. It seems like nothing has changed, right? But what if in the process a bird flies through? That changes things. So not all inverse operations are going to necessarily return you back to the value you began with. In example 6, we're going to be asked to verify that this blue function f of x and the purple function g of x are inverse functions. That means they undo each other. Think about addition and subtraction. Those are inverse operations. Think about the sine and the inverse sine. Those are inverse operations. Well, these are inverse functions. In order for us to verify that these are true, we are going to perform f of x upon g of x and see if x comes out, and then we're going to go in the reverse order. So for step 1, over on the left, if g of x is in purple, we are going to say f of that. So we are going to say f of 1/4 times the cube root of x plus 6. Now the f function says that we are going to take 4x cubed minus 6, and we're going to insert that wherever we see an x. So where we see that black x in step 2, we're going to insert the f function. So take a second to see how we've inserted f into g, and now we need to go about solving. So inside the parentheses, we have 4x all cubed. That could be 4 cubed times x cubed, and the negative 6 plus 6 go away, and so we come to this step. What do we do next? We take the cube root of 4 cubed and the cube root of x cubed, and then we're going to multiply 1/4 times 4. That's going to give us just 1x, and so sure enough, f of g of x leads us back to x. So if we plug any number in for x, perform g upon it, and then take that value and plug it into f, we'll come back to our original value. In step 2, we're going to reverse the order. We're going to take g of f of x. So what was f of x? That 4x cubed minus 6, and we're going to insert that into the g function. So we're going to say 4 times, wherever we saw that x, we're going to plug in the g function, cube it, minus 6. Now let's go with the order of operations. We can take 4 times 1/4, and we can take that cube root raised to the 3rd power, and we can deal with exponents. We still have the minus 6 at the end. 4 over 4 is just going to be 1. 3 over 3 is going to reduce to 1, so we're going to have x plus 6 raised to the 1st power. That's not really saying very much. That's going to give us just x plus 6 minus 6, which is just x. So if we can perform one function upon another and come back to x, we have inverse functions. Now let's put our work with inverse functions into play here in example 7. A worker in the produce department is asked to build a base to display a pyramid of oranges. The base should be square, and due to the lighting fixtures, there's a restriction. The height can only be 4.5 feet tall. The oranges are shipped in a crate that has a volume of 37.5 cubic feet. Can we help to determine the dimensions of the base? So the first thing we want to do is solve for s generically in the formula, and then we'll evaluate. So we should go back to geometry to remember that the volume of a pyramid is 1/3 times the area of the base times the height. And since our base is going to be a square, we can represent that as s squared. To work to get s by itself, let's multiply by 3, so we get the 3 in the numerator. Let's divide by h, and so we have s squared equals that expression on the left. We have one more step to do. We need to take the square root of both sides. Algebraically, maybe you should think that that should be plus or minus, but we're talking about the length of a side, so we'll keep the positive version. Okay, so now we have the formula so that if we know our volume and our height, we should be able to solve for s. So let's go ahead and use the information that was given to us. The volume is 37.5 cubic feet, and our height is 4.5 feet. It's usually not typical that we would use the feet cubed and the feet within the formula, but I put it there so that we can see how things unfold in just a second. I hope it will make sense. Okay, so just order of operations. Let's multiply 3 times 37.5. Let's divide by 4.5. And when we do that, we can also divide feet cubed by feet. And so underneath the radical sign is now 25 feet squared. That's the area of the base. When we take the square root, we'll come out to s equals 5 feet. So we've gone from something that was cubic, representing volume, down to square, area, and now we've got a linear dimension, s equals 5 feet. So when this person builds that base, it should be 5 feet by 5 feet. We hope those examples have been beneficial. Please reach out with questions. Your homework will be posted. Thank you.